Our next speaker is Marissa Lo, and she will talk about investigating the effect of varying magmatic volatile content on lunar magmatics and dynamics. Marissa, you can go ahead and share your screen.
There we go. Can you see that okay?
Right, yes.
Yeah, there we go. Okay, is the timer good to go? Thanks, yes. That's great. Okay, yeah, right, thank you. Hi everyone, thanks for coming along to this session. My name is Marissa Lo and I'm a third year PhD student at the University of Manchester. I'm working with both the planetary science and volcanology research groups here, and my research focuses on understanding volatiles in the lunar mantle using different volcanological techniques. So just to introduce the topic a bit more, the moon hasn't been volcanically active for at least the last 100 million years, possibly even the last 1 billion years. So techniques like sample analysis, remote sensing and numerical modelling are really key in unpicking what lunar volcanism was like. And as I'm sure you know, volcanism is a common process across the silicate bodies in our solar system, and it's really useful for understanding a wide range of questions. Such as how volatile rich was/is the lunar interior, especially in the context of the evolving giant impact hypothesis, a model of which is depicted on the left-hand side. It's really useful to understand how many volatiles were in the moon to begin with and what the situation is like now. Another question would be, how did magma ascend, and what were the key volatiles that drove ascent? In particular, lots of people are interested in understanding how the most dense high titanium magmas ascended, for example. Another question would be, what were lunar eruptions like? We know what the final eruption products look like, for example, the patches or dark mantling deposits that we can see in Alphonsus crater in the image on the left, but what was the duration and explosivity of the eruptions? And finally, did volcanic outgassing from explosive eruptions ever form a lunar atmosphere? And this is obviously an ongoing area of research with recent papers from Needham and Kring and Head and so on. So the overall aim of my research is to understand the role of volatiles in driving lunar magma ascent and eruption. In particular, the role of volatiles in explosive volcanic eruptions, which produce the pyroclastic deposits on the moon, and like the ones you can see in the image there. So to do this, the first part of my research involved adapting a terrestrial magma ascent model, which has previously been used to answer a wide range of different volcanological questions for volcanoes such as Etna and Stromboli in Italy. But as I said, I'm focusing on the pyroclastic deposits containing glass beads, which were found in the lunar regolith across all Apollo landing sites. So I've been using data on the glass's composition and volatile contents in my model. So from papers like from 2008, Alberto Sal's paper. And the model is capable of simulating magma ascent with magma containing two volatiles at once. So I was testing carbon monoxide and molecular hydrogen, and carbon monoxide and water. So based on redox conditions, molecular hydrogen is the more likely hydrogen species to be dominant in the lunar mantle compared with water. However, when I was adapting the model, I noticed that since water is the dominant hydrogen species in the Earth's mantle, there's a lot more information on, say, the geochemical properties, the solubility of water, all sorts of properties that I need for running the model. So based on this, I wanted to test water as well. Not only because there was more information about this, but I could also compare my results with the wealth of information on terrestrial magma ascent. And there's a few key strengths of this model to mention. The first one is that there's a huge number of parameters that can be varied, with over 100 parameters relating to temperature, composition, volatile behavior, viscosity, and so on. And the other main strength of the model is in its holistic approach. So magma ascent is a very complex process. A lot of the factors that govern it are interconnected, such as temperature change, change in rheology, whether crystallization is taking place or degassing. So yeah, main strength of the model is that it takes all of these into account simultaneously. Secondly, I completed a sensitivity analysis using a piece of software called Dakota. I did this to see what effect each of the input parameters had on the outputs. So in real terms, how much of an effect does, say, volatile content have on the way that magma ascends? And the main strength of using Dakota was that rather than me manually varying each of my model inputs and seeing what effect that had on the model outputs, the Dakota toolkit can test thousands of different combinations of the parameters and see what effect that has on the model outputs. So in fact, for each of the 5 end-member compositions of pyroclastic glass bead, I was able to complete 10,000 model simulations. So just to show a few of the results from this. So firstly, from the Magma Ascent model, I produced these gas exsolution graphs. So we have depth on the y-axis going down to 10 kilometers, and the exsolved gas fraction on the x-axis, which goes from 0 to 1. So the graph on the left is for the water and carbon monoxide model simulations, while the graph on the right is for molecular hydrogen and carbon monoxide. Just to go through the key, the dotted lines represent the minimum initial volatile contents I modelled, which again is based on literature and different measurements taken from the beads. The solid lines represent the maximum amounts I've modelled, and the different coloured lines represent either carbon monoxide in green, water or the hydrogen in blue, and the combination of the two in red. So I plotted these to see which gas was the more significant for driving magma ascent, and it seems that for the water and carbon monoxide simulations, even when we're having the maximum amounts of water dissolved in the magma, carbon monoxide seems to always be the main gas driving magma ascent. We see the opposite story with the molecular hydrogen and carbon monoxide simulations. Here, both volatiles are exsolving at great depth, creating a magma that's buoyed by both hydrogen and carbon monoxide. Moving on to the results from the sensitivity analysis, I produced this Sobel index plot. So one of the quantitative ways of showing the results from a sensitivity analysis is to calculate a Sobel index. So the greater the Sobel index, the more of a control the input had on a particular output. So here we have a plot showing, say, exit gas volume fraction and other model outputs against the model inputs, so pressure, temperature, radius, water, and carbon monoxide content. So like the Magma Ascent model results, we can see that water, shown in red, is not that significant in driving magma ascent or affecting, say, the exit velocity or mass flow rate compared with carbon monoxide, shown in brown, and especially not some of the other parameters, as you can see there. So for comparison, here is a Sobel index plot for the molecular hydrogen and carbon monoxide model simulations. And here the red represents the contribution of molecular hydrogen, and you can see it has a much greater contribution to the ascent and eruption conditions than water did. And this is likely due to the greater solubility of water in magma compared with molecular hydrogen and carbon monoxide. So based on my magma ascent modelling and sensitivity analysis results, for the water and carbon monoxide model simulations, carbon monoxide appears to have a stronger control on magma ascent dynamics than water. And for the hydrogen and carbon monoxide model simulations, we see the opposite. So generally, these results are highlighting the importance of understanding oxygen fugacity, composition, and other conditions within the lunar mantle. That was the main sort of deciding factor when I was adapting the terrestrial model for deciding which volatiles I was going to simulate. But it's not entirely clear how hydrogen would partition, say what proportions it would partition into between molecular hydrogen and water. So in all honesty, we don't know which results I've presented here are the correct answer. I imagine the actual ascent and eruption conditions are somewhere in between the two members I've been running here. So yeah, just as a heads up to finish up, I'm about to resubmit this work to JGR Planets after some revisions. So yeah, please check out the paper if you'd like to find out more, and thank you for listening.
Yes, thank you, Marissa. Thanks a lot. And we have time for one question, if somebody wants to ask.
Marissa, if no one else has a question, and please feel free to put questions in the chat, of course, as you have them. But Marissa, I was wondering if, I know that the sort of standard model for lunar magma ascent, or one of the standard models of lunar magma ascent, it involves very long dikes that reach a level of neutral buoyancy. And I'm wondering if your model sort of sheds light on how close those dikes actually have to get towards the surface before they become sort of, or at least the top mass of them becomes sort of self-buoyant from exsolving gas.
Yeah, I think I have tried to compare my work with those other models, and I think it's quite difficult because a lot of those don't necessarily have a scale attached to them. I think, it's more to do with, say, the amount of magma you have there, the dike thickness. So I think when I was testing this model to begin with, some of the model simulations didn't run, as in the magma wasn't buoyant enough for it to solve. So I think that probably provides like an upper bound as to how shallow does this magma need to be before it does ascend. So yeah, as I said in this, it solves for 10 kilometers depth and upwards. So maybe in future I could test how far I could push that.
Thank you. Very interesting.
Yeah, thank you, Marissa. And if anybody has a question for Marissa, please post his question in chat. So